All right, now, so we're going to briefly talk about the general structure for a depth-first search of a graph, okay? And we'll see that this is going to be used, it's like again and again, because we're going to have to traverse the graph and essentially make sure that we visit every single triangle, for example, okay? So this is idea depth-first search. So to traverse graph, or for example a tree, which of course is a special case of a graph, right? We have the option of a breadth first search, okay, where we first return the nodes which are sort of closest or most connected to the starting vertex. The origin vertex before expanding the search. All right, or we can do a depth first search. Okay, which first follows a path as far as it will go, right? Before returning to other closer nodes, okay? So in some instances, it's like you might prefer one over the other. It's like depending on the application. But since the main thing we're doing here is really to sort of just attempt to enumerate the triangulation, it doesn't really matter which one one uses, okay? I should also say that typically it's like on a tree, when you do these breadth first or depth first searches, you don't have to check whether you visited the node before. It's like just because the tree has no cycles, and as a consequence of that, it's like if you do one of these breadth first or depth first searches, you will entirely enumerate the nodes, it's like of a tree without repetition. Okay, so this is different when you have a graph, right, which has the potential for cycles, and so it's like what we'll see. It's like when we use these algorithms is that we'll have to mark whether or not we've visited a node before. Okay. All right. So we're going to adopt a depth first search approach, right? Okay, and then the algorithm looks like the following. Okay, it doesn't return anything, it's just a void, and it's a visit, and you visit a particular triangle in the triangulation. So you first check if, and okay, so first you have to sort of initialize it by making all unmarked. So, so if mu is unmarked, right, then you mark mu, and then you do some procedure which I label P1. Okay. And then for all the neighbors, okay, nu of mu, Okay, you do the following. All right, you visit the neighbors. And then once you're done this 4, you do P2. Okay, and else if the triangle, it's like, or the vertex or the node, it's like it's already been marked, you do P3, and then you end this if statement. Okay. All right. So that's sort of the general structure, and then it's like you'll see it's like in the algorithms which we'll actually do. It's like there are different things that's like will show up in P1, P2, and P3. So let me just say it's like in broad terms what those correspond to, and then as we go deeper, it's like into the algorithms for computing, things like orientability and the Euler characteristic. You'll see how these things play out. Okay, so P1 is basically just the number. It's just the steps to be executed when you first visit a node. Okay, P2 is what you do after you've processed all the children. Then P3 is the steps to be executed when you're revisiting a node. Okay. All right. So that's again this general structure of this depth first search, and we'll see it's like in subsequent discussions, this kind of structure show up again and again. Okay. So let me just stop here for now.